Hello, today I'm going to teach you how to write your own pathfinding script. Unity already has something called navmesh. I tried it, it wound up constraining the physics of my character. Then I downloaded a few other pathfinding systems. One of the ones I worked with was Polaris. Had all kinds of problems, so I decided to write one myself. I'm actually a novice programmer. I worked on it for about 48 hours, non-consecutively, and I managed to get one going that works for me. So that's what I'm going over today. I'm gonna leave a link to my GitHub with that project that I made public in the description below, so you can download it if you want to try it out. The code I wrote allows the soldier to walk around obstacles. And he can also walk around multiple obstacles in succession while going to his path. He can come at the obstacles from basically any angle and always choose the right direction to go around them. And if I click on an obstacle, the soldier will just go over to where the obstacle is and go to the point at the obstacle that's closest to the perimeter of where you stopped. Now, how I wrote this code is I started with a bunch of global variables. Believe it or not, all of these are necessary. Rally point is the point that the soldier goes to, and that's actually an empty game object, so that's why it's a public variable. Let's just get right into it. So I have a vector 3 called position, and that's what I use to input the new position of where the soldier is going to go. But at the start of the game, I got to make sure position is equal to wherever the soldier is already at. Then I have this enlarge capsule colliders of objects. That's all the way down here. What it does is it basically finds game objects with the tag avoid and then adjusts their capsule collider to a certain scale. We don't want to click like right next to the obstacle, and then since the measurement is from the center of the soldier, the sides of the soldier will actually bump into the obstacle. We want to maintain a perimeter. So expanding the capsule colliders prevents the soldier from bumping into the obstacle and also prevents us from clicking on any spot too close to the obstacle. So next we head down to update, and in update we check to see if there are any touches on the screen, and then to make sure we don't call these functions a million times, we go to touchphase.began. So it'll only activate when you first touch, not the whole time your finger's on it. So the first one is reassign rally point. We go all the way down here, reassign rally point. It has a raycast hit. It grabs the touch input. We got a new vector 3 that is equal to touch position. Then we do a screen point to ray, which basically goes from the main camera to exactly wherever you're touching on the screen. And this checks to see if it hit anything that you didn't touch off screen. And we change the Boolean path clear so that you can start moving. And we make the vector 3 new position equal to the raycast hit point X, Y, and Z. And then we check to see the game object tags. Right now I only have 2 tags for game objects. I have the ground tag for the ground, and I have a void tag for the obstacles. And so if you're touching the ground, we just immediately set the rally point position equal to this new position that we just made. Now, if you're touching a game obstacle, then the tag won't be ground, and we have to make a modified rally point position so you don't go straight into the obstacle. So we grab the obstacle by touched obstacle equals hit.transform.gameObject, and then we make a new vector3 direction to touched obstacle, which is just the position of the obstacle minus the new position. Then we have direction to touched obstacle.x is less than or equal to 0. We're calculating for radians using mathf.atan, and that's just the direction z over direction x. It's a basic equation in trigonometry to get an angle. And the problem is that the angle stops at 180 and then starts back over. And we want a full 360, or I guess whatever that is in radians. And so to do that, if it goes past 180, we just add 180 with mathf.pi. That's really just simple trick. Then we create modified rally point, and we create a float called collider radius, which is exactly equal to the radius of the colliders, because we don't want them going inside the colliders. We want them to be exactly on the perimeter. And then we have modified rally point.x equals math cosine radians, that's how far it turned in the circle, times collider radius, the distance from the center. And then we have to add the position of the obstacle.x, because that's how it knows where the center is to start the circle from. The y, I just left it equal to the ground position, which is 0.5. And then the z was almost the same function, except we use sine instead of cosine, and we use the touch position z. And then we make rally point.transform equal to position equals modified rally point, and that sets the rally point. The next thing we do is we go and we check the path. That makes sure there are no obstacles between wherever the soldier is now and wherever the rally point is. So we calculate the rally direction to rally point again, which it's actually doing an update later, but we want to make sure it's done right, and this could be called the first time. And so after we get the distance or the direction, which is just rally point minus the position of the soldier, we make a new vector3 called direction of aim, which is equal to rally point, except we add 1 to the y component. And the reason for that is the soldier's higher off of the ground than the ground is, and so direction to rally point is always aiming down slightly, and we don't want it to hit the ground and think that's the obstacle we're talking about. So after that, we do a raycast hit, physics.raycast, position of soldier, direction of aim, hit, and math infinity. And then we do hit.transform.gameObject.tag equals a void. So it'll only do this if whatever it hit had a tag that says a void. But it'll say obstacle detected equals true. That changes some things we do later on. And then it logs the obstacle. Up in the public variables, I made a game object obstacle, and hit transform.gameObject saves that in there. So now we go back up to our update function. We've already triggered the path is clear, is true, so it is immediately going to start walking. This continuously calculates the direction to the rally point, And then we got the distance to rally point, which is a vector 3 dot distance, rally point, and position of soldier. Then I made these two floats, ratio x and ratio y, and ratio z, and they calculate the direction of the soldier, the direction to the rally point in the x component over the distance to rally point. So distance to rally point is actually always in a, it's always going to be greater than this, unless you're going in one direction. But even if you are, the y position is actually always going to be 1. So even if you're right in the same spot, it's going to be down farther. So there's still going to be a distance between it. But what this does in getting the ratio is if you're coming in at an angle, it figures out which one's more than the other. And the nice thing about this ratio, since we didn't solve it for y, is distance is always going to be at least 1. So eventually the direction to rally point in any direction is going to drop to 0 in the x and z, but it's still going to be divided by 1. And that conveniently makes our math down here automatically stop, because we got ratio x times speed times delta time. And so whenever you are at the point you're supposed to be at, the ratio x just tends to 0 and it stops all movement automatically. We don't do that for the y component. We just want to keep it equal to wherever he already was. And we do it for the z component, then we add that to transform dot position, and it causes the soldier to move. But what if we trip the obstacle detected? That's in the check path function. Well, if that equals true, we got this global variable radius, which is the distance between the obstacle and the soldier's position. And if the radius is less than this, which is slightly smaller than the collider radius, I wanted to make sure the colliders were a little bit outside of this, because what's actually going to happen is I'm basically taking the width of the obstacle and the width of the soldier and then adding a little bit, because once this trips, it's always going to be slightly less. So if I didn't add this little number right here, then it literally would bump into the obstacle by the time this if statement gets tripped. But once that's tripped, path is clear equals false. And what that means is he's going to immediately stop moving because he's right next to the tree. Then the direction to center is the obstacle minus the transform position, and the radius is the distance. We calculate it again just to make sure it's correct. And then we use that same equation I just showed you in the other one with a tan of direction to center x over z, and of course we add 180 if it goes past a certain point. And then we have enter circle point equals transform dot position. So that keeps track of exactly where he started his loop around the circle. And the next thing he has to do is choose whether he wants to go right or left once he gets to the obstacle. And so we have this function, choose right or left. And the first thing we do is reset the capsule colliders. It's really not that hard. It's actually a repeat of the one I just showed you, except it's even simpler because we set the radius to 0.5. Capsule colliders, their radius is like a scale, is scaled by the scale of the capsule collider, or no, the scale of the object. So as long as you set it equal to 0.5, it's automatically going to be the exact same size as the game object. So we go back up to our choose right or left, and then the next thing it does is check right and check left. Now it adds 5 degrees to these global variables, angle right and angle left, and the angle right and angle left start at 25. The reason for that is sometimes it might glance straight past the obstacle and not even see it, and we don't want that to be an issue. So it starts at 25 and then it adds 5. This little quaternion Euler just lets it know to add the angle. Apparently this is in degrees, and we multiply that by the direction of aim. Then we do a ray cast for the new vector that we just created, and we don't go on forever because it might hit like another tree or something. So I just made this as a stopping distance for it so it doesn't check forever. It's a little bit past the scale. It's enough that it should be able to see the whole obstacle, but not so much it should hit other things. Now if it hits something, that means it needs to repeat, and so it's going to check again and add 5, and it's going to keep adding 5 until it doesn't hit something, and as soon as it doesn't hit something, it exits the loop. And check left does the exact same thing, except it's -5, starting at -25. Now the next thing we do is we evaluate which angle is greater, and you have to make a negative angle left because angle left is decreasing. And then it's either going to go counterclockwise or clockwise, and walking around obstacle equals true. So this starts the new thing in the update loop that tells it to walk around the obstacle. Then we reset angle right and angle left because it's going to use this every time it hits an obstacle, and we don't want it storing the old data. Then we do a calculate exit point when it stops circling, but we're going to cover that later. And then it restores the size of the colliders so that in the future you don't accidentally pick a rally point too close to the objects. So your path clear is no longer true, but we got walking around obstacle equals true now. And so we've got this thing called radians, and it's going to increase or decrease whether it's going counterclockwise or clockwise. And the radians, which have already been calculated, we just add delta time times speed minus radius. It's interesting that a radian, the circumference of one radian is actually the same distance as the radius, and so it makes the math really convenient that we just take the speed and divide it by the radius, and it keeps it going at the same speed while it walks around the path. Now for this, we use pretty much the same equation I showed you before with the mathf dot cosine radians times radius plus the obstacle position x, and then use the sign for z and keep your y the same because we're not calculating that, and put that equal to the transform position. Then we have an exit circle distance, which is a float, vector 3, the distance between exit circle point. Now how do we get that exit circle point? We go down here and we got calculate exit point. This is probably the most complicated part of the whole code, but all you really have to do is copy and paste it. This is basically a math equation that calculates the point that a vector intersects a circle. And it has an A, B, and C because it's like a polynomial equation. And I honestly copied this off of line, but it works really well. This is the quadratic formula right here. It's normally a plus or minus, but the interesting thing about this is the minus part is the point that we already have when the soldier stopped moving because he was too close to the tree. So you only have to get one of the two possible outcomes for that. Then the exit circle equals the new vector 3, and we just kind of put this into the equation, not using the y because this is all on flat ground. And then when we come up here back to our walking around obstacle, it's too hard to get it to go exactly to the point where the exit circle is. So if the distance is getting pretty close, you want it to stop right there, because it's going to calculate a new direction anyways once it gets moving. But we have walking around obstacle equals false, so that stops this while loop. Then obstacle detected equals false, which it might be found again, but for right now it's false. And path clear equals true, letting it know that he can start walking in a straight line again. And then we do our check path again because there might be another obstacle coming up right after that before you get to the rally point. And that's honestly the whole code in a nutshell. It's not perfect. I'm eventually going to have ups and down hills, so I'm going to have to modify the Y position. But for right now, this works pretty well. All I need my soldier to do right now is walk around trees. For my game, that's the only thing we need for pathfinding. So this is 266 lines of code. It's a lot simpler than all the other pathfinding scripts out there. If you get one of the other ones, then you're getting code you don't really need, which is adding to your file size. And then also, if you need to make really specific modifications, it's hard to really tell exactly what's going on in a pathfinding script you downloaded offline. But if you write it yourself, you know what works. Now, I don't know what game you're making. All I know is I'm a novice programmer, and I managed to write this to work for me. So you can use this as a base, and you can probably figure out a way to write your own pathfinding script too. It's not as hard as it seems, and you can just modify it to whatever your game needs. This will be posted online. Like I said before, the link is in the description below. It's on GitHub. I hope this helps some of you. Don't be intimidated by writing your own pathfinding script. It's not as hard as it seems. I only worked about 1 hour a day for a month and a half, and I got this done. Thank you for watching another episode of SS Street Fighter. Leave a like, leave a comment, and click subscribe to join the Street Fighter army. I'd also like to send a thank you to my Patreon supporter, Charles.